Hi everyone. If you're thinking about working with machine learning, you will undoubtedly come across two major algorithms called random forest and extreme gradient boosting. They are highly popular in online machine learning competitions such as Kaggle and often rank highly or even win these competitions. However, there has been very little research done on these methods in the presence of datasets with high multicollinearity, where independent variables highly correlate with each other. And so this project will investigate their performance on two publicly available high multicollinearity datasets. So let's get started. Firstly, I will briefly discuss the motivation for the project as well as the datasets that were analyzed and why I chose them. Then move on to brief descriptions of both machine learning methods. I'll then go over the pre-processing and exploratory data analysis of each dataset, and then finish up with the methods, results, and finally the conclusion. There was a very specific motivation for this project, and primarily it was due to the general lack of guidance for applied statisticians and machine learning enthusiasts in analyzing high multicollinearity datasets. And often practitioners resort to their favorite algorithm or randomly jump between them. I felt that this project would help provide a general recommendation to determine which of these two tree-based methods should be selected first in similar scenarios. There were two datasets selected for this project, abalone and wine quality, which are publicly available and can be located at the UCI Machine Learning Data Repository. Both datasets were selected not only due to their high multicollinearity, but also because there were no obvious irregularities with the data, such as missing data points, features with low variability, etc. I won't spend too much time on the inner workings of each algorithm, as there are plenty of online articles detailing them. But very briefly, to understand random forest and extreme gradient boosting, one needs to consider decision trees. Decision trees are popular predictive modeling algorithms where each internal node is labeled with an input feature, and the goal is to create a model that predicts the value of a target variable, the dependent variable, based on several input variables, the independent variables. Random forest pulls out a collection of samples while maintaining the class distribution. What is key here is that only a subset of the attributes are chosen at random for each tree built. This has the effect of preventing overfitting and mitigates against multicollinearity. Extreme gradient boosting, however, is a different tree-based method based on gradient boosting where trees are constructed iteratively and the examples are reweighted for each subsequent tree that focuses on reducing error. Extreme gradient boosting is a more exotic algorithm than gradient boosting, as it has additional elements that help mitigate against overfitting, such as regularization of base trees, approximate split finding, etc. The pre-processing of each dataset was considerable, despite being provided in a relatively clean format. The abalone dataset was found to be highly skewed in the numeric independent variables and extremely imbalanced in the dependent variable count of rings. To address this independent variable skewness, I decided to normalize using transforms such as square roots, and also to center and scale the numeric variables so that no specific variable would have an excessive influence on the dependent variable. The wine dataset was also highly skewed in the numeric independent variables and imbalanced in the dependent variable, wine quality. This was treated in a similar fashion, and again, normalizing, center, and scaling was conducted on each numeric variable in order to make each variable somewhat symmetric and of similar scale. Note that the normalizing, centering, and scaling does not affect the imbalance problem with the dependent variables, and I will address how I dealt with this situation during the methods section in a future slide. So after the pre-processing of the numeric variables, a correlation plot was constructed, and one can see that the data is still multicollinear using the brief interpretation notes here on the bottom of the slide. Indeed, the abalone dataset is extremely multicollinear, where the maximum variance inflation factor was found to be very large at over 150. The wine dataset was not as extreme, with a maximum variance inflation factor of about 9, and Usually, multicollinearity starts becoming a possible concern at about 5 as a general rule of thumb. So to summarize, each dataset was transformed from the raw provided data in order to ensure there was no undue influence from variables as a consequence of its inherent structure. Multicollinearity was sustained for the analysis. So when analyzing this transformed dataset, I used the software R version 3.2.3 and primarily used Random Forest and XGBoost R packages for the analysis. There were other packages loaded in the program for various other elements and dependencies, but these were the primary packages for the purpose of this project. In alignment with reproducible data research principles, the R code was submitted along with the project and the random seeds were set to 1000. When building both models, this needs to be done on a training set, and 75% of each dataset was used for the purpose. The final 25% of each dataset was used for testing, and indeed this subset is used for the final classification accuracy. Out-of-bag estimation was used for the random forest algorithm, and tenfold cross-validation was used for the extreme gradient boosting. And I will explain very briefly what these terms mean in the next slide. As you can see, the out-of-bag error is where each tree sample not used in the construction of the tree becomes somewhat like a test set. This out-of-bag estimate is given by misclassification error averaged over all samples. Tenfold cross-validation, however, is where each of the tenfolds is regarded as a separate test set and the average is used as the final performance measure. Another important consideration was the hyperparameters for each algorithm, and these are factors in each method that help optimize the performance on the dataset. Typically, these should be tuned in order to provide the best performance. However, extreme gradient boosting has more of these factors than random forest. Random forest had 2 hyperparameters tuned during the analysis, where extreme gradient boosting had 6. And in order to optimize this, it was much more computer intensive, and I had to end up using grid search methods. To address the dependent variable imbalance, I mitigated against this using stratified sampling. This ensured that each random sample had the same distribution as the original dataset. Now the results were very interesting, and I will dive into the specifics and then expand on whether the results obtained were statistically significant. For the random seed of 1000, the estimated test errors from the training sets calculated from the out-of-bag estimate on random forest and tenfold cross-validation on extreme gradient boosting, resulted in a smaller error for random forest on wine dataset, but a smaller error for extreme gradient boosting for the abalone dataset. The actual classification accuracy when the model was applied to the test set showed slightly different results, where the random forest provided the superior accuracy for both datasets. Now, when looking at the variable importance, both algorithms appear to show quite similar results. For the abalone dataset, and the weight-like variables appear to be most important in predicting the dependent variable ring count. This was followed by the dimension-like variables and then followed lastly by gender variable. For the wine dataset, there was no obvious clustering pattern. However, alcohol proved to be the most important variable in predicting the dependent variable, wine quality, whereas wine color was the least important variable. Again, note that this was for the random seed of 1000. Now, one interesting point to note was that extreme gradient boosting tended to weight variables more heavily, and as you can see, there was more variance in the relative importance for this random seed. However, to truly address the question that one method is superior to the other with these data sets, it is necessary to determine the probability distribution of the accuracy estimates. Now, this can be done by a method called bootstrapping, where the same algorithm is processed on multiple random seeds and the results collected. As can be seen from this table, there were different test set classification accuracies. obtained with different random seeds. The resultant distributions were represented as approximately normal, and a paired sample t-test was conducted on each dataset with a level of significance of 0.05. I determined that there was no statistical significant difference detected between the learning algorithms on the abalone dataset. However, I did detect a statistically significant difference between the algorithms on the wine dataset. In conclusion, I can state that the random forest proved to be a superior model for the wine dataset, but not for the abalone dataset. There was no real conclusion as to the effect of the multicollinearity, as the abalone dataset actually exhibited the most extreme multicollinearity of both datasets, and I couldn't detect any difference between the methods. It is very possible that the reason that the random forest proved to be superior on the wine dataset was actually due to the number of variables, and further research is recommended on this. Additionally, it was interesting to note that the random forest exhibited less variance in the variable importance measures than extreme gradient boosting, and again, I recommend further research be conducted for this phenomenon. Now, of course, in practice, it is highly atypical to use all independent variables in the final model, and feature selection methods such as principal component analysis is used to mitigate against excessive multicollinearity. Despite such methods, I did find that random forest was a very simple model to run, much simpler than extreme gradient boosting due to the hyperparameter tuning and computer resource intensive nature of XGBoost. And so I recommend running the random forest algorithm first in such datasets for these reasons. One can then attempt to improve upon this with feature selection methods and algorithms such as extreme gradient boosting, or even methods such as ensembles where machine learning methods are combined. Thank you for listening.